Hello and welcome to Lecture 61 of my class from Data to Decisions. I'm Chris Mack, and this time we're going to continue an example we started in the last lecture using logistic regression to predict who survived the sinking of the Titanic. So I'm going to repeat a few of the things that I mentioned in last time. Here's, by the way, a nice R-bloggers post on this topic where I got many of my ideas. A lot of good stuff on the R-bloggers website if you haven't discovered it already. First, we're going to install the package Titanic. It has the data that we're going to use, so I've already installed that package. And then we'll instantiate the library. Notice that when we look at our data, it's got some few things that are maybe hard to decipher the meaning of the variables. SIBSP is the number of siblings or spouses on board. PARCH is the number of parents or children on board along with that specific passenger. And then the codes C, Q, and S for embarked are Southampton, Queenstown, and Cherbourg, the different places where the passengers got on. All right, so let's load the data. There's a Titanic train for training data that we can load, and if I go look at that, we'll see all the different items. Passenger ID survived. This is the output, 0 or 1. 0, they didn't survive. 1, they did. 3 is the passenger class, first, second, or third class. Name of the passenger, gender, male or female. Age, where it's available. Notice here's an NA showing up in this spot, meaning not available. That's a standard marking that R uses to say a blank item or a not available item in a table. Here is a SIBSP. So you see sometimes 0, sometimes 1. Here's a 3. PARCH, parents and children, and sometimes 0, 1, 2. Ticket number, we won't need that. The fare, they paid for that. The cabin, if we had a map of everything that we needed, we could maybe use this cabin information, but we don't, so we won't. And then where they embarked. All right, so that's our data. Quickly, if you have a big data set, you want to know how big it is, you can use the dim command, dimension. So I'm going to just say dim of that, and it tells me it's 891 rows and 12 columns. I wanted to know just the number of O's, which is the number of data points. I can use length to give me that as well. Pick any one of the variables. In this case, I pick P class, and it will tell me that length. All right. As I mentioned in the last lecture, some of these data are blank. So here's a cabin where there's nothing there. There's a couple of embarked, etc. And that's different than this NA, not available. So a blank could be a character string that is just blank and that has some meaning that's different from NA, not available. In our case, it's not. It's just an inconsistency of the data. And one of the things that you're always going to have to do when you first bring in a data set is to check it out to see if there's any cleanup that is needed. Here, I've got blanks that should be NA. NA, if it's marked as NA, then R has a lot of routines that can handle seamlessly what to do about blank data, that is data marked as NA. So what I'm going to do is a command that will replace all the blanks with this R variable called NA. Note that NA is not in quotes here. I'm not giving a character that's NA. This is an R standardized variable, meaning not available. NA. So what I'll do is I'll make a logical statement. Data.raw equal blank. So this is a check. It's going to look for every single spot in the entire array, or that matrix, where the cell is a blank. Once it finds it, then I can take the data for that particular cell. So this tells me which cell it is. and then set it to be NA. And that one command will search all of those spots, replace all of the blanks with NA. So let's run that. Go back and look at the raw data. And now you see that all these things that used to be blank are now filled with this NA. So we've accomplished that task. Now that we've done that, let's ask ourselves, do we have a problem with too many NAs? This can happen sometimes when you just simply have too many blanks, and it really can cause havoc in your ability to analyze the data. I'm going to ask how many NAs there are in each specific column in two different ways. First, I'll use the sapply function, and then I'll use the colsums function. Sapply is a way to apply some kind of a function to something about the data. So I tell it what data I have, data.raw, and then I say I want to do a function on X. That means a function on the column, because every X is a X variable is in one column. So the function on X is going to be this. Has two parts. First, is NA of X. Right? So that will simply do a check. It'll go down spot by spot through the data and ask, is this particular cell NA? If it is, that's set to true. And then sum will sum up all of the times where that's true. So it will give me the count of the number of cells that have an NA in it. All right, so let's run that. And it gives me a listing of all of the column headers, and then underneath that listing is the number of NAs found. So passenger ID has no NAs, survived has none, P-class, name, sex. Age has 177. Now remember, there's 891 data points, but 177 of them are blank in the age, or they have NA, not available for the age. We see that the cabin has 687 of them, so that's the vast majority. We don't know where the cabin is. And 2 passengers don't know where they embarked. Well, 2's not so bad, but 177 is actually quite a lot. And if we have to keep this in mind, because if we decided to include age in our model, that means is we're essentially going to throw out 177 data points. We don't know their age. If we didn't include age in the model, if we included other variables like sex or passenger class or some of these other things that don't have any NAs in them, then we would be able to use the full set of data to create the model. All right, this colsums is another routine that does essentially the same thing. It sums up the columns. So what I'm going to do is do that is NA command again. It will set it to be true wherever it finds an NA, and then colsums will sum up all the trues each column. And if I run that, I get the exact same thing. So either one of those commands will do it. Here's another interesting thing we can do. We can ask how many unique values are there in each column. So again, I'll sapply function X, but I will do unique of X as the function, and then the length of unique of X. So unique of X will give me a list of all the unique values, and then the length of that tells me the number of unique values. So if I run this, find out unique passenger IDs there are. Oh, 891, one for every passenger, no duplicates. Survived, there's only 2, right? Because you either survived or you didn't. Passenger class, I see there's 3. There's 891 names. There's 2 sexes. 89 different ages. Here's one. SIBSP, there's 7. So they must, I'm guessing there's 0, 1, 2, 3, 4, 5, and 6. Same thing for PARCH, the parents and children. Some people had 7 parents. Well, 7 parents, but 7 children on board. 7 parents and children on board. We have 248 different fares, 148 different cabins, and 4 different embarked. Why 4? Well, there's the 3 cities plus the 2 something else as blanks, I guess. I'd have to go investigate. Where are those two? Where did they come from? Turns out I'm not going to use the embarked when it's all said and done. Okay, now we've got our data. We've taken a look at the basics of it. I do a little bit more investigating to make sure we understand what's going on in the data itself. All cleaned, all ready to go. Now, let's just ask a few very basic questions. What is the overall survival rate? Of all the passengers on board, what fraction of them survived? Well, I can calculate that in a fairly simple way. First of all, I can use this command. Sum of survived equal 1. So data.raw $survived is, of course, the column of the survived data. And if I set it equal 1, that's asking, it's a logical, the two equals means a logical equals. Is it equal to 1? If it is, set it to be true. And then sum all of those. That gives me the total number where this statement is true. I divide that by the length of that. Data. And that's, of course, 891, the number of passengers. So if I calculate that, and my next line simply prints it on the screen, the fraction of people who survived equals 0.384. So 38% of the people survived. That's a good thing to know just off the top, just to have a basic feeling for what's going on. 62% died, 38% survived. I can ask a question like, well, how many of the men survived? Well, how do I do that? Well, I do the same kind of thing, except for I have to use this logical and. Now I say, how many survived and how many of them were men? And then count those up, sum, count up the total that were both survivals and men, and then divide that by the total number of men. That will tell me what fraction of the men survived. So let's do that, and I see that the fraction of men who survived is only 19%. Half of the overall survival rate. I can do the same thing for women, and we see that their survival rate was 74%. Well, if you know anything about the history of the sinking of the Titanic, you know it was a women and children first kind of thing. Put the women and children on the lifeboats, and they got everyone on all the lifeboats. They either ran out of lifeboats, so the Titanic sank too fast, and they all couldn't get off. We can also ask, like, how many first-class passengers survived, how many second-class passengers survived, etc. So let's do that. Oops, sorry. I see I didn't type it in right, so this is second, and the next is third. So let's go and look at those. You see that the fraction of first-class passengers who survived, 63%. Fraction of second-class passengers who survived, 47%. And the fraction of third-class passengers who survived is only 10%. So that's an interesting statistic. So just by looking at these very basic things, what we would call marginal portions or probabilities, we can get a lot of interesting information. All right, let me do the same kind of thing in a slightly different way. I'm going to create a subset of the data. And I'll do this in a couple of ways. First, I'll use the subset command here. Subset of data.raw. And then I'm going to select 2, 3, and 5. So those are columns 2, 3, and 5. Columns 2, 3, and 5 are, let's go over here and take a look. Survival, passenger class, and sex. That's 2, 3, and 5. The C is a concatenate that simply creates a list out of those three. So this subset will allow me to create some tables that I want just with those three variables. Here's something that we don't really need in this case, but it's useful in many cases, na.omit. What that does is it takes whatever that matrix is and it throws out any row that has an NA in it, not available data. So it's just throwing out all except the complete data. Now in this case, I don't have any missing values for any of these variables, so it won't do anything. But that's a useful function to keep around because we often need to get rid of our NAs for certain kinds of analysis. All right, so now I'll add my data, my subset data called data.t, and I can do a few interesting things. So I can now grab this subset data, the data.t, and do a few interesting things with it. For example, table. The table command allows me to create tables. In this case, because I have 3 variables, it's going to give me 2 tables, a 2x2 table and then a second 2x2 table in the other variable. So the first one is a table of who survived by passenger class for the females, and the second table is who survived by passenger class for the men. You can see a lot just from this very simple table. For example, first class passengers in the women, we had 91 survivors and 3 fatalities. In the second class, we had 70 survivors and 6 fatalities. But in third class, 72 and 72. Right? Only half the women survived third class. So almost all female deaths came from the third class cabins. Now we go to the men, it's a very different picture. We see even in the first class, 77 did not survive. Only 45 did. So only about a third of the men survived in the first class cabin. It's worse in the second, and of course miserable in the third, where only 47 out of about 347 survived. We can do the same kind of things by doing prop.table. Prop will give us, instead of the raw numbers like this, the counts, it will give us proportions. But prop.table only works on numerical values, so I can't just give it the raw data. Instead, I will give it a table of the raw data. So here's a table of who survived, and if I do prop.table of that table, I get 2 proportions, the proportion who didn't survive and the proportion who did. Right? So here I see 62% didn't survive and 38% did. Likewise, I can ask, well, how many people were male? 35% female, 65% men overall on the Titanic. Proportion in each passenger class, I see 24% first class, 21% second class, and 55% third class passengers. All right, so these kinds of functions are very, very useful for just getting an overall view of the data itself. Now let's do some modeling. Let's do a logistic regression. I'm going to do a couple of things before that. First, I'm going to get rid of all the columns that I know I'm not going to use. Well, I can't use the passenger ID to do any regression. The name doesn't do me any good. The ticket number, not very useful. And because I don't know how to interpret the cabin information, and in fact, most of the data doesn't have cabin information, I'm going to get rid of all of those. So I'm going to create a new data set. I'll call it data.new that takes data.raw and only selects remaining columns, getting rid of 1, 4, 9, and 11. So let's do that. There, I've got my new data set. Before I do my regression, I'm going to do one of the things I very commonly do, and that's to look for correlations. I have a sneaking suspicion I know of one correlation. Passenger class, first, second, and third, I suspect is going to be correlated with fare, how much they paid for their ticket. Don't you think? Class costs more. So I would expect to see correlation there. Of course, I expect to see correlations with the survival rate, But I'm not sure I would see many other correlations like age versus sex or age versus passenger class or things like that. I don't know. We would have to look. So let's look. Here's what I'm going to do. I'm going to create a subset of this new data looking only at columns 1 through 7. Right, what's the new data here? Columns 1 through 7. 1, 2, 3, 4, 5, 6, 7. I'm going to just skip the embarked. I don't really care that much about correlations with where they embarked. So I'm going to take that out. I'm going to leave the rest. But to do that correlation between all of these, I've got to first convert the sex labeled as male and female into an indicator variable. To do that, I'll take advantage of a library called dummies. Create dummy variables. We're going to dumbify sex to be either a 0 or a 1. That is, create a dummy variable. All right, so I will create a new data set, data.indicator, that is a subset, just those first 7 columns. And then I'm going to take sex and create a dummy variable of 0s and 1s. So this command dummy will take that column, sex, and turn it into an indicator variable. All right, let's do that. Let's look at our data.indicator variable. So we see that sex has turned into a 0 or a 1 instead of male versus female. Now that we've done that, and we have only numerical values in our data set, we can look at a correlation matrix. So let me run the standard core command, C-O-R, for a correlation. It will create a correlation matrix of all the data. We can see, first of all, what correlates well with survived. Well, passenger class, sex. We have a sex female and sex male as the two options. Age, there are too many NAs in age, so you couldn't do a correlation because of all those NAs. Very weakly correlated with siblings and spouses, and a little bit more correlated with parents and children, but not much. And then quite a bit correlated with fair. You know what? I suspect fair is highly correlated with passenger class. So let's take a look. All right, here's passenger class versus fair, and that correlation is 54%, 55%. So we do see a strong correlation between fair and passenger class. We'll see the result of that when we do our regression because we'll only need to use one of these two. Of course, it's not a perfect correlation. There's a lot of pricing variability, I guess, between different cabins in the same passenger class. Looking around, you don't see any really strong correlations. There is a strong correlation between whether you had siblings and whether you had parents. In other words, if it's a family trip, you probably have some of both. Other than that, there's nothing really surprising or very significant in the correlation matrix that would maybe affect the way we do our regressions. All right, let's get back to work. Before we run our first regression, I'd like to use a couple of other functions in R to help us understand this idea of creating dummy variables, of creating indicator variables. And the first thing I like to do is show you the difference between characters and factors. All right, if I go to this data, you see sex is male and female. But these, in fact, are character strings. One says male, one says female. What we can do in R is convert character strings to factors. And so the factor would be named male and female, but internally treats it differently, this kind of a variable. So I can ask, is this data a factor? Because you can't really tell by looking at the table. But when I run it, it says false. that in fact the data in my data set is full of character strings, not factors. That's going to be important because I'm going to use this routine called contrasts. Contrast will show me how a factor is turned into dummy variables, indicator variables. But it only works on factors. Since my sex is a set of character strings and not factors, I have to first convert it to a factor. So I use this command called factor that give it the data.new $sex. In that column, it will turn it into a factor, and then my contrast command will show me how those factors of male and female will be converted to ones and zeros as an indicator variable. So let's do that. There it is. It will create a dummy variable that it will call male. If it's a female, it'll give it a 0. If it's a male, it'll give it a 1. Okay? So that shows you that contrasts how it works. It's a little bit more interesting to look at something like embarked because there's 3 levels, and so it's a little bit more confusing how it might do this. All right, if I go and run the levels command on factor of embarked, it shows me that there are 3 levels. Those levels are called C, Q, and S. Then I can run the contrasts to see exactly how that table is going to be generated for my 2 indicator variables. It's going to give me 2 indicator variables called Q and S. For C, the city of C, it's going to be 0 and 0 for both. For the city of Q, it's a 1 and a 0. And for S, it's a 0 and a 1. So these kind of decoder tables are very valuable because when I do the regression, and if I include these variables, this is how the regression software is going to dumbify the variables, and we're going to need to know that to interpret the coefficients, the model coefficients. All right, that's a lot of prep work just to get ready to do some modeling. So let's do some modeling. My first model, simple one, I'll take my whole data set and ask, how does survival compare to all of the variables? So I'm going to do the period here for the predictor variables, meaning give me one of everything. No interactions, but one of everything. So I'll run my model. I'll use GLM, generalized linear modeling. I'll set the family to be binomial, rank to be logit, so that this is a logistic regression. I run the model, and I give me next a summary of the model. So let's take a look. Well, we've got an intercept. Remember that model is log of the odds equals and then a linear equation. So we have an intercept, passenger class, sex, age, etc. These are the coefficients, standard errors, estimates, z-values, the ratio, and p-values for those. We see quite a few things. One, we see, for example, passenger class has a negative coefficient. That means as the passenger class goes up, numerically from 1 to 2 to 3, my probability of surviving goes down. Sex male, remember that it encoded this variable with a 0 and a 1, 0 for male, 0 for female, 1 for male. All right, the sex male gives me the hint that male is going to be the 1. So when going from a 0 to a 1, my survival rate goes down, and it goes down a lot. It goes down more than bumping up 1 level in passenger class. So that was a big factor. Age also has a negative coefficient, meaning the older you are, the less likely you are to survive. But it's a kind of a small coefficient, so you have to be a lot older before it makes a big difference. The sibling and spouse actually is just barely significant. It's reasonably significant, so that if you had siblings and spouse or a spouse on board, the more you had, the less likely you were to survive. And you might be able to explain that by saying, well, if you don't want to just hop in the boat without your family, your spouse, your siblings. So you try to find them, and then that reduces your probability of survival. All right, same thing for parents and children, but well, that is not a significant factor. Look at the p-value, 0.67. In fact, the fare also not significant. The embarked station not significant either. So those are a set of variables that do not produce significant effects. All right, we go back and check the correlations, and we see that these things are not much correlated with each other. Probably not a multicollinearity problem, and we'd probably be safe just removing all of those variables from our model. All right, we can look at confidence intervals of those coefficients as well. Here's the 95% confidence interval for each coefficient. All right, done with the regression. Almost always the first thing that everyone tells you to do is to plot. Plot the results, plot your data, plot. Take a look at your residuals, see what you see. That is not easy to do in a logistic regression. Let me show you. Let's do a plot. All right, let me do plot of model. This will give me 4 different plots. If I come down here and hit enter, here's the first plot. This is our residual. Residuals versus fitted. Wow, look at that. Does that look like what you're used to seeing with residual plots? Well, probably not, but it's the way residual plots look in logistic regressions. Remember that the true y value, the measured y value, is either a 0 or a 1. That's all there is, zeros and ones. The predicted probability is a probability that is a continuous variable between 0 and 1. So the residuals are always going to be some continuous variable between 0 and 1 as well. If the predicted value, the probability of survival is really low, then you expect the residual to be low, but it's always going to be negative because the probability of survival is going to be a positive number, where if you didn't survive, it will be negative. So all of these negatives are residuals for the case where the person didn't survive. And we have a lot of cases where I predicted a low survival probability, they didn't survive. I have a few cases where I predicted a high survival probability, and they didn't survive. See, the fact that they're spaced out more down here than over here means that our model is doing a reasonable job. Over here, all of these residuals are for the case of people who did survive. So my probability of survival that I predict with the model is smaller than 1. The actual value is 1, so I'm going to get positive residuals all through here. Again, down here, I've got a prediction of a high probability of survival, and they did survive, so that the residuals are small. And down here, the residuals are big. I'm basically predicting they won't survive, but they did. So hopefully what you'd see is these are spaced apart more. They're denser. Sort of see that. Nonetheless, these graphs are very difficult to interpret. How do we judge whether our model is doing a decent job if we can't use the graphs to help us? Here's one way that I thought of. Let's compare predicted to actual in the following way. I'm going to say my model did a good job of predicting if when I predict the survival rate is above 50% and they actually survived, I'll call that a match or a hit. If I predicted their survival probability of less than 50% and they actually didn't survive, I'll call that a hit, a match in prediction. So what I'll look for is how many times did I predict survival probability above 50% when they actually survived, and of course, they not survived as well. Here's what I'll do. Model $ fitted is the probability, the predicted probability of survival. So I'll do 2 times that, and then truncate it. Why do I do that? This is kind of my cheap way of cutting off that 50 percentile. So if you're above 50%, above a probability of 0.5, 2 times that will be a number bigger than 1, and when I truncate it, I'll get 1. If my predicted or fitted probability is less than 0.5, 2 times that will be less than 1. When I truncate it, I'll get a 0. So this essentially is converting my probability into a 0 or a 1 survival rate using a 50% cutoff. So that's my predicted 0 and 1. I'll subtract that from the actual 0 or 1. Then I'll call that y. And y will be either a 0, plus 1, or a minus 1. But only if it's a 0 did I get a hit. That is, I survived 0, 1 matched my predicted truncated 0, 1. And then my hits will be the sum of all the y equals zeros. In other words, how many times did I get it right? All right, so let's run that. I have to run this. I forgot that I was running the. I forgot to run the small data set. So I realized that a number of my model coefficients were not significant. So I'm going to create a new data set where I only keep significant variables, and I'll run a new model with all of the significant variables, and you see that the non-significant ones have been eliminated from my model. I forgot to run that before coming down here. And if I go and take a look at now the y's, the number of hits, and the hit ratio, the number of hits over the total number of passengers, what do I find? Let me type in hit ratio, and I spelled it wrong. Try it again. Hit ratio, and I get 0.808. In other words, 81% hits. Again, it's a little bit arbitrary to say this 50% cutoff means if I'm on one side, I survived, I'm on the other, I didn't. Nonetheless, that is one way of comparing your predictions to the actual. And the fact that my hit ratio is 81% means I'm doing a reasonable job of predicting. All right, last thing to do here. Let's exponentiate our model coefficients. I won't go into this, but if you look at the math of how a logistic regression is set up, of course, it's the log of the odds. If I exponentiate the log of the odds, I get what's called the odds ratio. So I can run that on all the coefficients, and I get an odds ratio, each of these. So let's look at one of these, for example, sex male. The odds ratio is the odds of survival for being a man divided by the odds of survival being a woman. And the fact that it's 0.07 means that the odds is, what is that, 15% or so? 15 times less likely to survive if you're a male versus a female. The odds of survival anyways. Age almost 1, meaning for every 1 year in age, there's not a whole lot of difference in your survival rate. Passenger class, the odds ratio is 0.26. So for every time I change my passenger class by 1, the odds is about 4 times worse than it was in the, say, first class compared to second. I can do the exact same thing, including confidence intervals. So I can look at the odds ratios that we just looked at, now add confidence intervals around them. All right, there's tons more to do to play around with this regression, but that's enough for this time. Till our next lecture.